Welcome back. When we talk about making AI go faster, our minds immediately jump to the GPUs, right? These huge, powerful computing engines. But what if the real bottleneck, the hidden anchor dragging down your whole multi-million-dollar project, isn't the processor at all? What if it's the plumbing? Today, we're diving deep into the supercritical and, frankly, often overlooked world of network infrastructure for AI.
Okay, just a quick heads up before we get started. This is Module 5 of a 15-part tutorial, and it's based on a really comprehensive report by Virtualization Options LLC. Now, what we're talking about today is for general guidance. It's not a warranty, and it's definitely not legal or financial advice. We always recommend you chat with your own financial, technical, and legal pros before you take any action. We're really just scratching the surface of what's in the full report.
So here's our game plan. First, we're going to uncover that unseen AI bottleneck. Then, we'll dive into something I'm calling the all-reduced data tsunami. You'll see why. After that, we'll check out how cloud providers handle this for training, see why inference is a totally different ballgame, and wrap up with that classic tug-of-war, speed versus security. All right, let's get into it.
First up, the unseen AI bottleneck. This is all about why the network you're probably used to is just completely unprepared for what high-end AI is about to throw at it.
I want you to really think about this for a second. Imagine you've got the most powerful GPUs money can buy. We're talking tens of thousands of dollars a piece. They're all revved up, ready to crunch data at light speed. But what if they spend most of their time just waiting? That's the reality when your network can't keep up.
And this slide right here, wow, it just drives the point home. On the left, you've got your standard corporate network, maybe 10, 25 gigs per second. It's like a quiet country road, totally fine for normal web traffic. But on the right, that's the AI training network. We're talking 400 plus gigabits per second, using specialized stuff like InfiniBand. It's not just a faster car, it's a rocket on a superhighway. They're not even in the same league. It's a totally different world. Which brings us to Section 2, the all-reduced data tsunami. So why do you need this insane amount of bandwidth? Well, it's all because of a very specific and very chatty communication pattern that's at the heart of training big AI models.
And that method is called data parallel training. The idea itself is pretty simple, actually. If you want to train a model faster, you just make a bunch of copies of it, give each copy its own little piece of data to work on, and let them run at the same time on different GPUs. But the magic and the massive networking challenge is how they all stay in sync.
And that brings us to the all-reduce operation. So after each GPU chews through its batch of data, it has to share what it learned, these things called gradients, with, and this is the key part, every single other GPU in the cluster. This isn't a one-on-one chat. It's a giant all-hands-on-deck conference call where everyone talks at once. They all share, they all average out the answers, and only then can they all update their models and grab the next piece of work. This quote just nails it, doesn't it? If the mathematicians can't hear each other clearly or have to wait for the slowest person to shout, the whole team grinds to a halt. The entire cluster of processors can only move as fast as its slowest conversation. That's the bottleneck. And the sheer amount of shouting is, well, it's staggering. For a pretty standard 64 GPU cluster, that all-reduced step can generate around 2.5 terabytes of network traffic. And get this, that's not a one-time thing. That happens every few seconds. Your normal office network would just fall over and cry.
So, the bottom line here is simple, and it's painful. When your network can't handle this data tsunami, your incredibly expensive, power-sucking GPUs do nothing. They sit there, idle. They finish their work in a flash and then just wait and wait and wait for the network to catch up. It's like you bought a garage full of Ferraris, but they're all stuck in rush hour traffic. You're just burning money.
Okay, so the problem is massive. Let's talk about the solution. Section 3, Cloud Networking for Training. How are the big cloud providers actually solving this data tsunami problem?
Well, the big three have all built their own specialized, high-octane networking just for AI. You've got AWS with its Elastic Fabric Adapter, or EFA, pushing up to 400 gigs a second. Azure has instances with 200 gigabit InfiniBand, and Google Cloud's A3 instances have something called GPU Direct TCPX, which is custom-built for exactly this kind of GPU-to-GPU chatter. And let's be absolutely crystal clear about this. These are not optional luxuries. They are not nice-to-have upgrades. If you plan on training a large model on more than one server, these networks are 100% essential. Without them, your performance won't just be bad, it can actually get worse as you add more machines, because all that communication traffic just completely drowns out any benefit you get from the extra GPUs. Now, it would be easy to think that you just need this fire hose of a network for everything AI related. But that's not true. When we switch gears from training a model to using it, what we call inference, the rules of the game change completely.
And this slide lays out the difference perfectly. Training, on the left, is all about that sustained brute force, all-to-all bandwidth between GPUs. But inference, on the right, is a lot more like a regular website. It's a simple request-response. A user asks a question, the model gives an answer. For that, you don't need massive bandwidth. What you need is low latency. You need that answer to come back instantly, because every millisecond of delay is a millisecond the user is waiting.
Which brings us to our final section, performance versus security. This is the classic balancing act, because when you push for the absolute maximum network performance, you can sometimes open up some new and interesting security challenges. I mean, look, securing your AI stuff is non-negotiable, right? Your models, your data sets, that's the crown jewels. So the standard playbook is to build a fortress around them with virtual private clouds and encryption. But here's the rub. Some of the very technologies that give us this incredible speed, like one called RDMA, work by essentially creating a high-speed shortcut that bypasses the normal network layers and all the security checkpoints that live there.
So this creates a really tough question for anyone designing these systems. How do you lock down a network that is specifically built to bypass the normal rules for the sake of speed? You can't just apply the old security playbook. You have to think differently and find new ways to monitor and control these super fast data paths.
Okay, so let's wrap this all up. What are the big things to remember? Number one, your network is not a commodity. It's a critical piece of your AI performance puzzle. Number two, that data tsunami from distributed training is real, and it needs specialized networks to handle it. Number three, inference is a different beast. It cares more about low latency than raw bandwidth. And finally, number four, going for hyper-performance can create new security headaches you need to plan for.
So I'll leave you with this final thought. As you're planning out your next big AI project, you need to ask yourself this question. Is the network you're building going to be an accelerator, letting your GPUs fly? Or is it going to be an anchor, silently dragging down your performance and wasting all that investment? The choice you make could be the difference between success and a very, very expensive failure.